Hello, and welcome to this Open Systems Media webinar on the top 10 ways to mess up your distributed system. I'm Mike Demler, Editorial Director for Open Systems Media's online publication, dsp-fpga.com, and our monthly dsp-fpga.com digest. I will be serving as the moderator for this webinar. First, a brief introduction to our topic today. From their direct experience working with hundreds of teams, building thousands of complex distributed systems, RTI has seen common mistakes that sometimes even the best designers have made. The challenge of developing these systems is growing from just a few distributed computers to thousands, and soon even millions of connected devices. In this webinar, RTI will share their experiences so that you can learn how to avoid these common mistakes. Now, before we get started, I have just a few housekeeping items. Today's presentation will consume about 50 minutes, leaving us 10 minutes or so for questions at the end. There are several on-screen buttons for you to take notice of. First, by clicking on the Enlarge Slides button, you will be able to view the slides in full screen mode. You will also find a button on your screen to download a copy of the slides. There's a Forward to a Friend button that you can use to send an email to a colleague inviting them to join us for this live event. Finally, you will also find on your console window a button that allows you to enter questions in real time. We'll do our best to address your questions during the closing Q&A session. If you have a question pertaining to the webcast operation itself, one of our technicians will respond back to you during the presentation. We may not get to all of your questions before the end of our allotted time, but in that case, someone will get back to you after the webcast with more information. Finally, this webcast will be posted online within 48 hours, and an audio podcast will also be made available. We'll have more details on that at the end. So on to the presentation. Our speaker today will be Stan Schneider, CEO of RTI. Stan is a recognized expert in the development and integration of distributed real-time systems. He founded RTI to develop productivity tools for the real-time marketplace. Under his guidance, RTI has grown into a multinational business with offices throughout North America and Europe. Stan completed his PhD in electrical engineering and computer science at Stanford University, where he is also a graduate of their Advanced Management College. He also holds a BS in Applied Mathematics and an MS in Computer Engineering from the University of Michigan. Over to you, Stan.
Thanks, Mike. Great. Welcome, everybody. My name is Stan Schneider. I'm from Real Time Innovations, RTI. And this webinar is the top 10 ways to mess up your distributed system. So RTI has been in this business for quite a while at this point. We have literally worked on hundreds of operational systems out there and worked with a lot of our customers, ranging from applications and military systems such as Navy ships. We have a Aegis cruiser here. We've actually been working with the radar system of that for quite a while, and now with other operations on the ship, and more recently with some of the newer ships like LCS here. We've done quite a bit of manufacturing kinds of applications. Schneider Automation, for instance, uses our technology in their PLCs. We have quite a few unmanned vehicles. In fact, a lot of the experience in this comes from our position as the platform architecture chair for a program called UCS, which is Building Unmanned Systems Architecture for the United States. We also worked on many other kinds of unmanned systems. We have quite a bit of experience in telecommunications. There's also the car down there is Volkswagen, which is working on technologies for what they call driver safety augmentation. It's got radars and lidars and things around the outside of the car watching what's going on and helping you avoid collisions. And we've also worked with large systems such as medical imaging systems, which produce an amazing amount of data in a very short period of time. systems that must remain active 24/7, 365. For instance, air traffic control down in the bottom left there, as well as things like monitoring assets or tracking the train traffic, for instance, going up and down the East Coast. And lots of different kinds of consoles and displays and radars. What puts these systems together is they're all, what they have in common. First of all, they're all mission critical. Most of them are truly real time, or they really need to work on time, not just correctly. And they're seeing a huge, as time goes on, a huge data explosion and scaling problem in one dimension or other. And we see that as the driving problem in our industry. So, it wasn't too long ago that the real-time distributed system or network system was a box with a bunch of cards plugged into it. Today, almost all of them are on networks, and there are multiple things plugged into a network. They may have tens or even hundreds of nodes. We're seeing many more what we call systems of systems, where you have a well-defined, developed system that are put together into a much larger combined system. And then, we're seeing in the future, and more increasingly, the need to take those operational real-time systems and connect them into the enterprise data management systems and business intelligence and things like that. So, the real trend in the industry is driving a lot of the problems is a greater volume of data, exploding data volume, data speeds, and really system-to-systems integration. And so we've noticed over time that there's a problem that people run into. And the problem is, when you're starting out, you design an infrastructure, and then you have to design each of the pieces for the infrastructure during develop, sort of assuming what that infrastructure is. And by the time you get the whole system developed, if you have a problem with that architecture, it's sort of too late. Because it's very hard to go back and change that infrastructure. And it's, that makes the horrible assumption that everything starts at the same time and ends at the same time. In reality, it's a process where you're adding things in, evolving subsystems and things like that, and you really can mess up in many ways. And so we humbly submit what we have found is the top 10 ways to mess up your distributed system. So that's the topic today. So I'll jump right in. The first one is to gloss over your data model. And by a data model, first of all, many people don't even realize they have a data model or don't think of it that way. But by a data model, I'm really just talking about all the types and schema in the system, coupled with the understanding of the sharing requirements of the data. So, if you misunderstand the data structures, that's a problem. But because without a good understanding of the structures of the data model, all of the applications will develop their own models. And then sending information between entities becomes an exercise in translating at every step, and it just makes the system hard to deal with. I've got an example here of a different kind of approach. This is something called FACE, the Future Airborne Capability Environment. It is a effort going on to define an avionics platform in the U.S. And they're putting a lot of effort into building what they call the core data model. I'm not going to go through this or anything here, but the point is, if you are trying to build a big system, and they're not trying to make all the pieces exactly use the same data model in every node, but they are trying to have a clean, crisp data model that you can use across the system, across an industry. And it doesn't need to be industry-wide. Even small systems should start with some reasonable analysis of the data content and exchange requirements. You need a data model. Even if it's not perfect, at least it's going to be a good approximation, and that good approximation is pretty important. From this, you have to exchange data, usually exchange data over some kind of messages being sent around. Some designers think of their messages as the data model. I don't think that's a very good way to think of it. Messages are really a view of the data model, and there's no one perfect message. There's many different kinds of things to send around. So really, I suppose the point here is you should first figure out what you're talking about rather than first figuring out how you're going to talk, and it makes the communications much easier to deal with. So that's sort of the first step, and the first way to mess up is to skip that step. A second way to mess up is to misunderstand your data flow. So once you know have a rough idea of what you have in the system, how you're going to send it around, you need some clarity of how that's going to work. So if you build it without flow clarity, you can run into choke points. You can waste an amazing amount of resources. You can have reliability problems. You can have startup problems. You can have all sorts of things. The real risk here is to choose an overall architecture that really doesn't fit your problem. And most complex systems have many different kinds of flow requirements, so you have to be somewhat flexible. But if you choose an overall architecture that doesn't fit your requirements, it makes things pretty bad. You'll get scalability problems, and I think the most painful realization you can make late in a design, late in the game, is that the fundamental architecture isn't going to work. And we see, the networking world has evolved a lot in the last few years, and we see lots of different kinds of data flow models. There's, sort of the old way is point-to-point. Think TCP, or if you don't want to talk about networking, think of a telephone. Point-to-point connection is basically a one-to-one connection. You have to figure out who you're talking to. Once you're talking to that person, or that node, that application, you have a very high bandwidth path between the two. The problem is everything gets shoved down that same pipe. The TCP, for instance, if you send a large message, it will block the pipe until that message is through. If you have an error drop or something, it's going to retry that, and all communications stop until it's done. So basically, it's easy. There's a nice standard out there with TCP/IP, but it's not. It doesn't branch, and it makes the system not very clean. In the 80s and 90s, client-server and centralized databases and brokered ESBs and things became very popular. They allow branching, which is really important. You definitely have a whole different ability to communicate within multiple nodes and things like that. Corba and DCOM and things like that are all in this kind of a structure. It's great if the information is naturally centralized in a database. If it's not naturally centralized, then you've got a single point of failure. You get performance bottlenecks. It's difficult to fail over if you lose that server. And then publish subscribe, which has been around for a while, but it's very much more performant. Every communication path has a logical, independent path to take, so you don't have any crossover or bottlenecks. It branches very nicely. In the real world, things like subscribing to a magazine or even just watching a television channel is a way of subscribing to the kind of information. It's great for many, many communications. It's great for things like failover. It is, in fact, in the real world, all news media does this because it is really a good way to send time-critical information to exactly the places that need it exactly when they need it, which is really important. And then there's a new technology. It's really called data-centric publish-subscribe, which is also, it is publish-subscribe. It has a bit of a difference in that the infrastructure itself takes on more responsibility for making sure that data is available in the way that the applications want to access it. And I'm going to talk about this some more later, but it really is a new future direction. There's a standard out there for data-centric messaging by the OMG Object Management Group called DDS. RTI is by far the largest vendor in that market. Just full disclosure. But we see it really as the future of an awful lot of the kinds of mission-critical large systems that we think are becoming important. So the third way to mess up when you're building a distributed system is to allow uncontrolled state. And the best way to think of that really is, what is truth? Even in an undistributed system, it's very hard to know what truth is sometimes if you've got a lot of different parts of your application that you're building. In a distributed system, it gets a lot worse because every application, every node, they're all different. If they all start storing state, it becomes inconsistent. If they all have their own version of how to resolve that inconsistency, it becomes really hard. An overall, an unstructured distributed application has a lot of state, and none of it's well understood, and it really can destroy a lot of the ways you're thinking of how to build the system. It makes it, brittle. It's inconsistent. There's lots of ways to break. There's lots of difficulty in even understanding what's going on. If you've worked on distributed systems, even the very simple thing of what time is it is not a well understood thing a lot of times, because every node has a slightly different version of what time it is. But there are many, many very complex pieces of state in a complex system. And fundamentally, if there's no simple, robust way to agree on truth across the system, it becomes a big problem. And the key way to fix that, this is the data centricity I was talking about, is to have a controlled way to think about state. So, database's key benefit is, for instance, a database is a stored technology, obviously. It sort of contrasts to unstructured mishmash of files and static variables and caches and things like that. A database came along as a data-centric storage technology and changed the way that people think about state because it's an accessible source of consistent truth. You have a database. If everybody accesses that database, you always know that you all have the same view of truth. And there's an interface to that that's much simpler also. It's sometimes called CRUD, create, read, update, and delete. It's a clean conceptual interface where you can create information and you can change it and you can get rid of it, and everybody sort of sees the same interface. The opposite of that, the other alternatives have thousands of different kinds of operations with unclear or unknown semantics, and having a few well-known defined one makes a big difference. So database is a well-established technology in the storage space. In the communications realm, data-centric middleware really does for data in motion what a database does for data at rest, at least conceptually, in that there's a single source of truth. The middleware actually takes the responsibility for providing that truth to the node. It's somewhat much more complicated in a database because that truth has to be actually proactively pushed to the right places, and there's a whole bunch of issues around what happens if the node goes down or the communications doesn't work, or the capabilities of the different participants in the system. Some may be capable, for instance, of high-performance, reliable communication. Some may be small nodes that just can't store their information or whatever. But the middleware is going to take responsibility for a single source of truth. It imposes or allows a known structure in the data, so all the nodes and the tools and everything else can introspect and know what data is on the network. And then there's clear rules for accesses and changes and updates. So you can, for instance, very clearly say, I want to be updated at least once every 200th of a second, and I want to be notified if that doesn't happen, and all those kinds of things you can set ahead of time. And middleware, just like a database, once it's set up and you've defined your tables and structures and schema, it will enforce that. You can't go and break that in an application. The middleware will also enforce what you've said you're going to do. If you're a publisher and you say you're going to publish 500 times a second and you don't do that, the middleware is capable of saying, this node has broken its contract, and we'll out and fix that. So I do want to quickly contrast data-centric middleware with most other kinds of middleware, which I'll call message-centric. In data-centric middleware, the middleware itself is a source of truth. It will basically be attempting anyway to make sure all the nodes have the same information. In a message-centric thing, the middleware is a source of, it may be very reliable, but it's a source of reliable messages. The messages themselves are the first-class citizens, which is also useful, but it's a very different kind of interface, and in our humble opinion, doesn't give you as much control or power in building complex systems because you don't have as clean of rules for how the state evolves. So, moving along, the fourth way to mess up your distributed system is to ignore evolution. Distributed systems are anything but static in our experience. Your data model, even if you do a good job of it, will not stay fixed. Versions of your software will change. Applications will join and leave the system. Your existing software and independently modules will be integrated. You may have to, reuse the whole system or pieces of the system later and hook up legacy modules and things like that. It's an even greater challenge than with most applications, even complex applications, because in reality, especially if you've got a system that once it's up and running has to stay up and running, you can't update all your applications on all your nodes at the same time. So in reality, while the system is running, you're going to have a mix at any given time, and you need to have some understanding of your data model and flow, but it's also really important to plan for change. And even if you do plan for change, the crush of integrating all these different applications over time very often overwhelms all of your strategies, and you need to have a way to think of how you're going to support evolution going forward. And there's, this is a really hard problem, don't get me wrong. There's many different kinds of ways to evolve models and behaviors. The first one is, basically just make sure the infrastructure itself is extensible. So, for instance, in RTI's middleware and DDS standard, the data types on the network are typically known. There's a thing called type codes that allows you to understand what's on the network. It makes evolution much simpler if your applications can be smart about knowing what types they're dealing with. It also makes it much easier to do things like integrate tools. One example we have actually integrated by writing a little daemon that runs inside Microsoft Excel, we can subscribe to any data, any numeric data anyway, on the network and populate Excel spreadsheet cells with it. And that daemon doesn't need to know anything about the types on the network because it's actually got all that information available. Many kinds of middleware actually do that. They'll send out self-defining types. The problem with that is it's slow. You have to send it with every message. We actually have a discovery process that makes it much easier to figure out what's going to be there ahead of time and then promises that it will be the same thing. But that just, that's sort of the base. As systems grow, those types may change. If they change a little bit, there's actually a new portion of the DDS spec coming out that does extensible types. It lets types change a little bit, so you can have slightly different versions of them on the network, and it still works. But it's much better than the alternative, which is having the applications manage it. We do see, especially as customers coming from different backgrounds, wanting to send opaque blobs across the network. Opaque blobs have the advantage that everybody can pass them around. They have the huge disadvantage that you lose all information to all the nodes in the system of what's really going on. We see, sending blobs is really a sign that you don't really understand your data model, and it has some really nasty and implicit coupling between nodes. So that, that will help you at least keep a tightly integrated system working as it evolves. But then, you're going to have more complex integration kinds of problems. And for instance, routing, if you have two systems or multiple systems with, significantly different data models, where you want to do something like only export certain parts of the data from this system, and you're going to, what's called guarding, only allow certain values, certain data types or data information to get out. You can do that. You can transform between fields, map between fields. And then, as time evolves, there's, in the enterprise world, well-established ESB, enterprise service bus technology, and that kind of technology is showing up now even in high-performance real-time systems, which will do, routing and guarding, but also transformation and mediations, and truly allow a real-time service-oriented architecture, so a structure out there. And we're excited about that. We think it's going to really make a big difference in the ability of people to field different kinds of applications even. So the fifth way we see people, the fifth way to mess up your distributed systems, and this one is somewhat non-intuitive for a lot of people, is make all your communications reliable, or in fact build it on top of a technology like TCP, for instance, that requires that has a lower level reliability, infrastructure. And the problem with reliable delivery is the way, especially unless you have a purely reliable network, which are rare out there. Reliable delivery means you have to retry if you have an error, and retrying takes time, and therefore reliable delivery means unreliable timing. And that's actually a pretty complex trade-off. Sometimes you want reliable delivery if you're building a big system and you are recording everything that's going on. You're some kind of a logging system, then you may not care when you get the data, and it's more important to get it. So, retry me as much as possible until I get the data. On the other hand, if you're, really high-performance real-time system, for instance, if you're a military system trying to shoot down an incoming missile, where that missile was a few samples ago is no longer nearly as relevant as where it is now, and you don't want the old data retried. You want the latest and greatest. So, you really need to know how to react to failures in a different kind of level of technology or level of thinking. So I'll give you an example here. This is my favorite example because they keep lots of information. This is an asset tracking system out there that is started out with a transactional design using some pretty standard middleware techniques where every communication between every node was designed to be very reliable. So a transactional system basically says, I've got an update, and then the receiver says, send me your update, and then sends the update, and the receiver confirms the update. And it's great for a way if you're handling money or something to make sure you never pay anybody twice or you never miss a payment. The problem is when you're trying to track thousands and thousands of things, and real time isn't important. For one, it can't be done with multicast. And so this system, was only able to do about 12,000 tracks. It ran on a platform with 11 servers, 88 cores. They had reliability problems. 1.5 million lines of code, so SLC as far as lines of code. It took them many years to develop, depending on how you count. And then, they switched over to a DDS-based design, and, they got 25 times the performance. It actually can run, even though they want it for redundancy, don't want to run on a single core, but it can do all of that on a single core. And a lot of this is a, testament to the inefficiency of the previous design. But, DDS, our technology can do full redundancy. It can do multicast Instead of sending careful communications to each node out there, it can send out a blastogram that goes to many different nodes, and then still be able to deal with reliability if some of those nodes don't get the information. So it's a much simpler system, and by giving the middleware the capability, the responsibility for maintaining that truth, it cut down the lines of code by orders of magnitude. And of course, that's not, it's not the same level of truth, but it was what this system really needed. Much more simple way to build the system. So sixth way to mess up your distributed system is to wait till the end to figure out how you're going to integrate everything. There's a famous quote, I'm not quite sure who said it, the schedule will never again look as good as it does today, which I love that quote. It's absolutely true. And why is that true? It's because, most systems, especially as they get more complex and larger, their development time becomes more and more dominated by the system integration at the end of the program. And if you approach that with no strategy, it gets much worse. And there's many ways to look at that, many ways to do it, but if you think through ahead of time how you're going to do the system integration, it makes a big difference. And my poster child, or one of them, application for this is one of the LCS ships here. This is one of the Navy's newest ships. I think that picture's almost a year old now, something like that. But it was designed both to be a fast ship, but also to be developed faster than others. And to do that by integrating many different kinds of technologies, legacy systems, legacy protocols, new technologies, new applications, and really started from the beginning by defining the interfaces between them carefully, and really looking and understanding the coupling you're likely to get, so you can reduce that coupling. And so you need to be able to think through questions like what happens if I add this application? What if I turn this thing off? Which order do things have to start? How fast does this module need data? Even more subtle things like when do the peers of this application find out that something has failed? Those kinds of reliable and time interactions are insidious coupling. They're often not thought through at the beginning, and they're not addressed by usual treatments. And a way to address that is our tech. We have this concept called quality of service, QoS. And the concept is that there's producers offer quality of service. So I can offer how fast I can publish, or how reliably I can publish, or how quickly you can assume I'm gone if I stop doing things. And consumers, subscribers, can request their levels of quality of service. And then the middleware actually goes out there and during the discovery process decides whether or not these things are going to work. And if they are going to work, it matches it up, and you start communications, which is great. So even from the start, you've at least got both sides to agree they're going to have the communications you need. I think even more importantly, if one of the participants violates its contract, so it said it could produce it quickly and it doesn't, or something like that, if there's a violation of what's going on, the middleware actually knows about that, and sometimes it can't fix it, but it can at least notify everybody. And in a highly reliable, mission-critical system, it's often more important to know something is wrong, and you need to react to that fact that this data is no longer reliable than almost anything else. And so that really helps with system integration to have that level of definition of interfaces beyond just what information you're sending. All the other things that are usually implicit. If I just create an API, for instance, I could call that API once an hour. I could call that API once a millisecond. Those are very different. This kind of approach lets all the pieces know how fast they can expect data and what happens if that data it doesn't come at the same time. So it makes a lot of the sort of hidden aspects of an interface much more explicit, and then at runtime enforces that, which makes a huge difference. So another way to mess up your system, is to think that performance or scale isn't important. It's not my challenge, or it can be done later, or it's easier to get than you thought. I'll just broadcast or multicast everything, and that will get me the performance. And if it's not reliable, I'll knack it, or I'll ask for it again or something. Just those kinds of approaches we have found to be much trickier than most people go in thinking of it. Or even, there's a spec in the power industry, I think, that just says, try it 5 times. If it doesn't work after 5 times, then it's not going to work. It's a news thing. But if that doesn't work, you've sort of got a problem because, a lot of times when things fail, they're going to keep failing for a while. Anyhow, performance and scale is really important. Many programs, while they think performance is important, don't even have a performance requirement. If they do have a performance requirement, they don't know where it came from. Most of them don't really have that nailed down, and I think it's actually difficult to define at the beginning of a project anyway. But I will say unequivocally that a system with fast infrastructure is fundamentally more adaptable than one without. A fast infrastructure can handle slow systems. A slow infrastructure doesn't really work that way. So, and you often don't find those performance challenges until the end. Fundamentally, there's an apocryphal, I don't know if it's true or not, story that, I don't know if it was Michelangelo. Somebody asked the sculptor, how did you make that look like David? And so I just looked at the block of stone and I cut away everything that didn't look like David. And that sounds funny, but actually is the way a lot of people think they're of doing performance. They'll just take out whatever's slow or tune it out later. And in our experience, tuning a slow system often doesn't work. If you want to build something fast, you need to design it from day one to be fast. Because really the way you get performance is by avoiding sources of delay, and that sounds easy, but it's anything but. We have worked very hard on many, many fundamental technologies like memory allocation, not allocating memory in the loop, queuing technology, buffering technologies, ACK storms, NAC protocols, many, many strategies that have to be figured out to make sure the system remains performant. And scaling issues are very subtle. We actually see people with serious scalability problems with just a few or maybe tens of nodes or applications out there. And there's many different, think of scaling as having lots of different nodes to talk to, but there's many different ways that scaling becomes a problem. Memory use, if you're using sockets, connect times, or the fact that you have to, reconnect and go through the whole TCP state machine to do that. And there's heavyweight sessions, and you get too many sessions going on. And the really subtle problem is you add some small load to a system that's been running for a long time, and that small load crashes performance or throughput, and the whole thing grinds to a halt. It's a lot like on a street, on the road, the traffic jam, the real cause of the traffic jam out there is the traffic itself. Many times you get to the front of the traffic jam, and all of a sudden the road's wide open, and that's because the throughput crashes when you get too many cars on the road, and it's very nonlinear. And if it's unexpected, it can really mess up your system. So, each additional load takes some performance. Subsystems that worked well in test might work great as you put 6 or 7 together, or 20 of them together. When you add that 21st one, suddenly the system stops working. And you can't blame the 21st one. it's an overall system property, and it's very difficult to think through later if you haven't started out with the design to have the performance and scalability you need. So the eighth way to mess up your system is to not anticipate things that may not be on top of your mind when you're designing it as an architect. No system was in isolation, but in today's world, these systems are becoming much more connectable than they were in the past. Many designers realize that, but don't really appreciate the business driver of mining your data for lots of purposes in the future. I can give you some examples here, but actually Gartner, a big analyst firm, has been pushing what they call ITOT, informational technology, operational technology, convergence, and they basically claim that any organization that does mission-critical kinds of things will risk failures if they don't really think this through. So I've got a good example, a recent example for us. So this is a system built by Siemens Wind Power. Siemens is the #1 world generator or builder of turbines. These things are huge. They're like 18 stories high, 100-meter blades. But this is, we started working with them. It was a very typical application. What they really cared about was, grid control. Sorry, we have a. But it was, high performance tuning of the turbines and making sure that they are communicating correctly. And it was a, pretty typical kind of application. Lots of turbines out there. They have to communicate with each other to do things like manage wind gusts and things through the farm. But they also had another problem in that they wanted to really have control over their business. Predictive and preventive maintenance. Some of the sensors, for instance, in a turbine is the temperature of bearings and things like that. And when you see the temperature going up, that bearing or something's wrong in that turbine and it's going to fail. And they want to send out a maintenance crew, especially if the thing's out at sea, as in this picture, has to get in a boat and go out there. And you want to be able to maintain, if you've got 500 turbines in your farm, you want to go and fix all 17 of them in one trip. And that's an important and hard thing to do if you don't have the ability to take your real-time system and mine that data for those little pieces that need to then go into your diagnostics programs and your business intelligence systems to make this thing work. So, anyway, so the ninth way to mess up your distributed system is sort of assume that all implementations of the standard are the same. And full disclosure, we're the leader of the DDS standard. There are other DDS vendors out there, which is great. It's a nice competitive market to some extent, but they're actually very different, and I encourage you to take a look at that. I'll just use an analogy here. All of these vehicles are street legal, but they're very different. You should really ask things when you're looking at it. How reliable, how much experience does this vendor have really building systems out there? What configuration parameters does it have available? What services are available, extensions and tools and support and testing and things like that really make a big difference. 80% of distributed code, for instance, is error handling, at least in the middleware, and none of that's in the spec. And so you really should take a good look at what you need from your system and look at the different vendors out there. So the 10th way to really mess up your distributed system is to, I'll sum it up as go it alone. Go it alone, there's sort of two ways to go it alone. The first one is to stick with what worked for you. So 100% of our customers are not building their first distributed system, and that means they have some technology they've been using, and it may well work for the next generation of their systems, but things are growing very quickly, and all these factors are combining to make that less and less viable going forward. So if you go ahead with what you've had in the past, you may find that insufficient for the next 5 or 10 years or whatever the lifespan of your system is. And the other way to go it alone is to ignore really what work and the experience out there that other people have. And so this is my favorite picture of that. This is from a trail in Hawaii. And you look at this and you say, wow, that's scary. But what it really says to me is many people have been down here. There are many hard lessons that they've learned, that they've found places where you can mess up. And the vendors out there, RTI in particular has experience with hundreds and hundreds of applications. I'm sure some of them have relevance to what challenges you will likely face. So things like, if you thought through retries and persistence and guaranteed delivery and timing, but also you might not find out until system integration time that your transactional kind of protocol technology isn't going to work. We'll find this to be useful. And so the 11th way to mess up your distributed system is to believe there's only 10 ways to mess up. And we find new ones all the time. People ask why we should care about whether you have experience. It's basically because we've failed more than you have. We've seen many people fail. We have failed many times, and in that you gain experience that helps you going forward. So I haven't talked about RTI at all here. RTI's Real-Time Innovations. We're the leader of data-centric middleware. We have something like 70% of the middleware market share, according to the analysts. We support many standards. DDS is the biggest one, but many other kinds of standards in the networking and middleware world we have experience working with and connecting together. We very much encourage and drive standards, including at OMG. And we have lots of experience out there. So just reviewing top 10 ways to mess up. You should really think about what your data model is. Don't just assume that's going to evolve out of the system. Think through the data flow and its implications for the fundamental architecture of the network. You really need to, as system designer, have some controlled way to manage state and controlled way to think about how to evolve the system. Reliability is more than just delivery reliability. Reliability has many dimensions. System integration strategy is something that really needs to be thought through from the beginning. Performance, a high-performance system makes it much more flexible, has a lot more ability to adapt than starting with something that isn't high performance. Don't forget the business drivers and take advantage of the experience out there in the market. So in summary, I started out with, the problem is really by the time you figure out if your infrastructure is good, it's too late. That's really due to the increasing complexity, and what starts out good enough might not end up being good enough. And the solution to that is really a philosophy more than anything else. You need to proactively manage complexity. The system has complexity. You can't really get rid of it. You can choose where to put it, and that is a proactive choice that you should think through. Simpler systems, even simpler systems have this problem. But if you have a very simple system that you're going to develop quickly, it's only going to last a year or two, you're not going to intend to reuse it, then simple messaging might be enough. But in a larger, complex system that has to evolve over years, that would put all the complexity in the applications that are connecting together, and that can be a real problem. So you need some more advanced technology to do that. The whole point around data center infrastructure, and if you've ever used it or if you're going to use it, I will be the first to admit or state that it's going to take you a little more time up front to figure out how to design your data models and communications and interfaces, but the benefit of that extra effort up front is to pull complexity out of every application, and over time, that's a big win. And finally, leverage proven technology and experience. And that's the presentation for today. We do have some time for questions.
Thanks, Stan. Yes, we do have time for questions, and I'll remind the audience once again to use the window on your screen if you have a question and get it into the queue. For our Q&A session, Stan will be joined by Gordon Hunt, the Chief Engineer at RTI. Gordon is also RTI's Principal Consultant for Distributed and Interoperable System Architectures. Okay, so let's go to the first question. My existing protocol works and is proven. I want to use this as the baseline for my system integration exercise. Are you saying that this won't work?
Well, it depends a lot on your protocol and your ongoing needs. As I said, 100% of our customers have some existing protocol or distributed infrastructure, whether they built it in-house or they're using Corba or something like that. Some of these designs are really weak. The worst ones don't even have a communications layer. They're just calling networking code from inside their applications all over the place. Some of them are very sophisticated, very well thought through, well supported by internal teams. If there are certainly places where a focused, purpose-built infrastructure makes a lot of sense, especially if it's highly specialized needs. But, that's an example of what I call going it alone. If you go it alone, you're going to spend a lot more time on your infrastructure, and, the industry is moving ahead very quickly. It's unlikely you're going to move ahead as quickly. We've seen a lot of it before. And, our other users are forcing us to look at problems that you don't have yet but may have soon. Good example, we have flow controller, in our technology. If you, put a lot of data on the network or very large data, we can help you put that onto the network gradually or delicately so that it doesn't overwhelm the network. Other things can still go on. You may not think you need that today, a year from today, or 2 years from today. Maybe you want to send video data or something around, and now you've got a problem. So, it depends a lot on what you're trying to do, but, I would encourage you to at least look at what else is out there before deciding to go it alone.
Okay, the next question is the data-centric middleware like a policeman trying to enforce what data is out there? Is an update always needed if new data comes in? Is it like a policeman? It's sort of like a policeman. I mean, when you join the system as a participant, you agree to a contract of sorts, and if that contract, as long as you follow that contract, it's fine. If you violate that contract, then your contractees will be notified that you're out of spec with your own contract, which is bad. But your second part is an update is always needed if new data comes in. There's many, many, many ways in the system to decide when you're actually going to get the update. One of the most important things to do with a network, I probably should have had this as one of the ways to mess up, is to get the right data on the network and not the wrong data on the network. So, for instance, you can do things, if you've got a big system with 50 different users, and every one of them, or many of them, have different data requirements, you can subscribe to parts of the data. It actually has something called content filtering. So you can say things like, say you're an air traffic control station and you want to put up on your screen for your operator the flights in your area. You can say things like, I want to subscribe to aircraft within 5 miles of me, below 10,000 feet,
descending and coming towards me. You could actually make that kind of a filtering request, and the middleware would then only send you that information. So, is an update always needed if new data comes in? That's up to you. As a subscriber, you can decide whether or not you want to send that data. And one of the things that our middleware does, and as far as I know, no other one does it yet anyway, is we can do writer-side filtering. So if nobody wants that data, we won't put it on the network at all. And we can be smart about only sending the data you want. So we can be judicious users of the precious bandwidth in the system. And sometimes that becomes really important, especially if you're going over a wireless link. But even over a high-performance link, you want to put only what's on the network, what's really needed by somebody on the network.
Okay, next question is asking, could you elaborate a little bit on what you mean by truth?
That's a difficult question, even not in a technology sense. What you mean by truth in a distributed system usually is eventual consistency, but what we really mean by truth is a source of information that is agreed upon by all members. It's not, there's databases, for instance, have ACID properties, if you know that has a very crisp definition of truth, is, how things are updated. Most distributed systems don't need that level. It's very difficult doing a distributed system anyway. But the truth in the system is really the ability to, within parameters that you can set, know how reliable that data is. So, for instance, if I subscribe to the temperature of a boiler, here's a really simple example, and maybe I'm going to do something like set an alarm off if that temperature goes over 300 or something like that. Then truth is the temperature of the boiler. But if I stop getting updates, the truth is I don't know the temperature of the boiler anymore, and maybe I want to shut down the system that's heating it anyway because I've got a potential safety issue. So truth doesn't necessarily mean I know the data in a distributed system. That's often hard or impossible. But truth means I have a known view of what that data really is. But that's, as in the philosophical realm, truth is not easy to find. But we actually do a pretty good job of defining it compared to other kinds of technologies.
All right, we have next question. Could you compare and differentiate DDS with a SOA model that uses, excuse the acronyms, EDA, XML schema, and canonical data model? Sounds
sure.
Like there's a lot to compare there.
Yeah, there's a lot to compare there. Actually, I don't.
Perhaps you want to take that offline?
No, I just need to refresh so I could read this question here.
Okay.
So, SOA model, we very much support SOA architectures and, DDS, just like in an enterprise JMS or SOAP or whatever, is a transportation technology that enables SOA. It really isn't SOA by itself. There is not really there's no requirement, for instance, to use XML for things. DDS has its own, actually has a very flexible way of defining data types, but it also has a flexible way of discovering those things. Actually, Gordon's online. Maybe he wants to add some color to that.
Can everybody hear me?
Yeah.
Okay, great. Thanks, Stan. I think fundamentally, I'm assuming EDA here means event-driven architecture, and the differences between a SOA architecture and an event-driven architecture. Fundamentally, they're kind of the same thing. Folks look at SOA and they say services are stateless and they interact with this distributed information bus. Well, the information bus, even in a SOA architecture, has state, and the event-driven architecture is propagation of that state. So it's two views of the same kind of thing going on in a large-scale distributed systems. The functions and how I want to develop and deploy these units of function effectively, these services, and how these services connect and interact with the information flowing around in the bus. With regards to modeling and capturing the information of that flow, that state on the bus, and there's many ways to describe the schema of the information, the content. XML, people use XSD, and I could probably list off a variety of other data model standards and information modeling standards for the schema of the data content. However, Stan's talk, really the difference and what the more important thing about an actual data model is that you're also capturing the context. When is the information relevant? What does it mean to miss it or not miss it? The behavior aspects and the relation aspects of the data, and then describe how that data is represented on the wire and moved around and acted on by the different services. So fundamentally, we can describe a certain set of behaviors that capture a particular state update as more of an event. I mean, this thing is a one-shot. It's a state update. The state persists over time. I'll update it again when it changes, versus a service interface interaction with some sort of transactional type command pattern. So I have to execute commands in a linear order. My favorite nautical example is open hatch shoot missile. Those actually do matter when you start talking about order of execution. And so again, while I'm thinking about service interfaces and functional kinds of transactional exchanges of data, fundamentally on the wire, there's still behavior associated with the messages that are flying around, which are effectively events as well. So they're different views of the same fundamental distributed data-centric architecture.
Hey, thanks, Gordon. Unfortunately, we've run out of time for today. Thanks to our participants for all the great questions. If we didn't get to your question, somebody will follow up after the webinar. I want to thank our presenters, Stan Schneider and also Gordon Hunt, for helping out with the Q&A, and thank RTI for this informative webinar. This webcast will be posted online at the URL shown on your screen within 48 hours. Note that an audio-only podcast version will also be available, and you'll be able to search for embedded_ECast on iTunes, where you can find all of Open System Media's eCasts that are available for you to download as MP3s. Thanks for everybody and their participation, and thanks for attending. Have a great day.